Hey AP Stats, it's Mr. Lineski. We're looking at goodness of fit test, chi-squared test, chapter 26. The weird thing about this one, we're going to go through the 4-box method. So box 1, the hypothesis, we're usually going to look at these. It's typically easier to write it in words. We're not really going to have symbols like P and mu anymore. So the example that I made up was that if we were checking if students' zodiac signs and birth rates are distributed evenly, the idea is that we're kind of running multiple one-prop z-tests. So like I could do a one-prop z-test for each zodiac sign, but then I'd have to do 12 tests, and that takes a while. So it's easier just to kind of lump it all into one group and then do one test for it. So the null here is always as a reminder saying kind of what really doesn't shock us, and so we kind of expect it to be distributed evenly. Sorry about that. To see if they're distributed evenly. Whereas what would shock us is if they aren't distributed evenly and we're like, oh, there's more Scorpios out there than, there are Capricorns, something along those lines. So that's sort of what the ho-ha looks like here. So now the conditions, these conditions are going to be the same for all 3 types of chi-squared tests. So I'm only going over goodness of fit on this video, but we'll talk about the other ones in the next video. So the first condition is basically just stating that you have counted data, that the data that you have is a frequency of some sorts, and so you might say something like, we have counts of people's zodiac sign, or the different types of zodiac signs. The random condition is still pretty much the same. We're checking for a random sample. And then we have something called the expected cell frequency condition. It's kind of like our NP-NQ condition, saying that it's greater than or equal to 10. We're not actually using that, though. Basically, we're just checking that each cell has an expected value of at least 5 individuals in each cell. Kind of looking through the mechanics. So for the mechanics, there, again, as I mentioned, 3 types of chi-squared tests. So the first one is the goodness of fit. This is all we're focusing on today. So how do I know if something's a goodness of fit? It's if there's one variable with one sample. And we're going to look at an example of a problem here in a moment. When you run this on the calculator, you're going to essentially get 3 things. You're going to get a chi-squared value, you're going to get a p-value, just like we always do, and you're going to get the degree of freedom. For goodness of fit, degree of freedom is equal to the number of categories minus 1. That will change for the other 2 chi-squared tests, but for homogeneity, just still sort of like n minus 1. Conclusion's still going to be based off of our p-value. We're still going to reject the null, fail to reject the null. We either have the evidence for the alternate or we won't. Alpha level still will be at 0.05 if we are not specified. One thing I want to point out here is that the chi-squared graph, so we sort of had our normal model and then the t model. The chi-squared model is skewed to the right. And when we actually get chi-squared, that value is kind of telling us how far off are we from what we expect. So the higher the chi-squared value, the more likely you are to reject the null. So like as chi-squared gets bigger, your p-value kind of gets smaller. So let's take a look at what this looks like. So we have a company claims that each batch of its deluxe mixed nut contains 52% cashews, 27% almonds, 13% macadamia nuts, 8% Brazil nuts, and we're going to test the claim. Quality control inspector comes in, takes a random sample of 150 nuts from the latest batch, and we basically want to see, are they consistent with their claim? Is it really 52% cashews? Is it really 27% almonds? Etc. So the idea here is that we're giving counted data, but we need to figure out, well, what is the expected data? What do we expect to happen? If the claim truly is happening, what we do is we take the sample size, so this 150 is our n, and if 52% of the sample truly is cashews, then we would expect 150 times 0.52, we would expect there to be 78 cashews. So you go through and you do that for each of the categories. So for almonds, macadamia, Brazilian. And so kind of what does this look like? So we are just doing a goodness of fit test. So for box 1, our hypothesis, remember what wouldn't shock us? What wouldn't shock us is if the sort of mix is consistent with what they claim. So it's basically just like, yeah, you're doing what you say you're doing. Cool, that's what we expect. Whereas the alternate is sort of saying, no, it doesn't. It's inconsistent with what they're claiming, or it's not meeting their claim. So that's what shocks us. So that's what the hypothesis looks like. So for our conditions, what are we given? We're given the different count of the types of nuts. All of our expected values were above 5, so you do need to list out the expected values, so that is right here. So make sure you're listing those out. And then here we're told that the sample of 150 nuts is random. Conditions have been met, therefore we will run a chi-squared goodness of fit test. And so what you're going to do on the calculator is you're going to enter this into list 1 and list 2. So the observed goes in list 1 and the expected goes into list 2. So we're going to pull up the calculator here. So on the calculator, like I said, we're going to go to Stat, Edit. In list 1 is where we put the observed values, or in other words, what we see. And then in list 2 is where we put what we expect. And this is where you can actually just type out the math for that. So like you can do 150 times 52%, and that will give you the 78. You don't have to like calculate it and then type it in. So now we're going to go to Stat, we're going to go over to Tests, and then if we go to letter D, what I do want to point out is notice that there's option C, chi-squared test, and option D, chi-squared goodness of fit test. We are going to run the goodness of fit test. So it is important to be able to tell the difference between the tests. So then this just asks for observed and expected, so list 1, list 2. And then degree of freedom is just, well, how many categories did we have? So there were 4 different types of nuts. So that minus 1, so degree of freedom is 3. And then just hit calculate. And that gives us our values. So chi-squared, P, degree of freedom, and then this thing CNTRB. I'm going to talk about what that is in a moment, so just ignore it for now. So you don't need to write that part down, but here are our mechanics. We'll use an alpha level of 5%, and so what would our conclusion be? Conclusion would be that since the p-value is greater than alpha, 8% is bigger than 5%, we will fail to reject the null. There's not enough evidence to support that the deluxe mix is different from what they are claiming, or that it's inconsistent. So this idea of CNTRB, these are the components. In other words, they're kind of like a residual. We calculate that for each individual cell. So the idea is that we have a count for cashews and then an expected count. And we're kind of finding what is the difference between those counts. And if you recall when we did scatter plots, this was called a residual. But we kind of had positive and negative residuals, but then we always squared it, our R squared value. So same thing kind of happens here. We have to square it to deal with the negatives. So to calculate each of those things individually, we do the observed minus the expected squared, and then we divide it by the expected value. And this essentially just tells us which of these values was furthest off. So the bigger the component is, the more it's affecting your chi-squared value. So if you're looking at the data here, which one kind of threw us off the most, it looks like almond, 29 to 40.5, but if we go and look at the calculator, so our first value was 0.32, so that's not too bad, and if you scroll over, the next one was 3.2, and then the one after that was 0.01, and then after that was 3. And so it really was the almond that kind of had the largest component. So that was kind of throwing us off. Alright, so that is it for Goodness of Fit video. Thank you for watching. I know it, now you know it.